Look, I'm about to tell you something and you're going to think I'm making it up. That's fine, most people do it first. But stick with me because once you understand what I'm actually talking about, you're not going to be able to look at a map of the world the same way again. There's a continent sitting at the bottom of the Arctic Ocean right now. Not a myth. Not some conspiracy theory floating around Reddit. A real continent with coastlines and valleys and the kind of geology that takes hundreds of millions of years to build. And it's been down there, hidden under ice and sediment and darkness, for longer than humans have existed. We're talking about tens of millions of years. And nobody knew. Not because geologists weren't looking, but because it was literally invisible, hidden in data we couldn't read, written in a language we didn't speak yet. Gravity whispers, magnetic whispers, signals so subtle that for most of history, we just didn't have the tools to listen, we didn't have the equipment, we didn't have the satellites, we didn't have the algorithms. We were basically deaf to what the planet was trying to tell us. But then, something changed. The tools got good enough, the satellites got sensitive enough, the computers got fast enough, and suddenly, scientists started seeing something that shouldn't exist, something that made them go quiet in the middle of looking at their data. And when they called their colleagues when they said, "Hey, can you check this because I think I'm seeing something impossible?" Those colleagues checked it, and they saw it too. That's where this starts. Before we continue, a quick note. We started this channel because there are thousands of incredible stories hidden beneath the surface of our planet that almost nobody talks about. Lost worlds, forgotten oceans, entire landscapes erased by time. If that's your kind of thing, consider subscribing. It's free, and it genuinely helps us keep making videos like this. All right, let's keep going. Let me start with the sentence that will have you doubting me for a second. Gravity is not the same everywhere on Earth. I know you should have learnt this in school, but nobody really talks about it. I know how it sounds. We have all learned that gravity is this fixed thing. It keeps you on the ground, it keeps the moon in orbit, it keeps the entire solar system in motion. The apple on Newton's head. Gravity is gravity, right? Except it isn't. At the small scale, at the level of mountains and ocean trenches and continents buried deep underground, gravity changes. Every spot on this planet has a slightly different gravitational pull depending on what's underneath. Dense rock pulls harder than light rock. That's what we were taught in physics. But the difference is impossibly small. We're talking about measurements so tiny that for most of human history, we just didn't have equipment sensitive enough to measure them from space. Fractions of fractions, numbers so small they're basically meaningless unless you have the right instrument. And for most of human history, we didn't. Then came satellite gravimetry. In low orbit, a satellite doesn't need to touch anything. It just floats there, close enough to feel the planet beneath it. Close enough that dense rock underground actually pulls on it, just barely, just enough that scientists can measure the shift in its path. That's how you map what you can't see. That's satellite gravimetry. For decades, this was theoretical. It was a cool idea, but not practical, mostly because the instruments weren't sensitive enough. The processing wasn't fast enough, and the computers weren't powerful enough. So for a long time, it was all theory and promise and maybe someday. Then, in the early 2020s, the someday came. NASA launched GRACE-FO, the Gravity Recovery and Climate Experiment follow-on. This wasn't just another satellite. This was a purpose-built instrument designed to detect the tiniest gravitational variations. The European Space Agency had GOCA, the Gravity Field and Steady-State Ocean Circulation Explorer. They had multiple space agencies and multiple satellites, all pointed at one goal: map Earth's gravitational field with insane precision. We're talking about precision that would have been impossible just 10 years earlier. Precise enough to see through water. Precise enough to see through sediment layers thousands of meters thick. Precise enough to read what's actually down there beneath the Arctic, beneath the ice, beneath the layers of rock that nobody has ever seen. Scientists fed the Arctic data into new algorithms. And what came back didn't make sense, not according to what we thought we knew. The Arctic seafloor was supposed to be young. That was the textbook answer. That's what they taught in geology classes. Young ocean floor, thin crust, light rock. But the gravity data said something else entirely. The Arctic had something underneath it that was way too dense, way too thick, way too old. And that was the moment some scientists started asking a question that sounded completely absurd. It had all the properties of ancient continental crust, not young oceanic crust. Something that had absolutely no business being there. Something that made scientists stop and stare at their screens and wonder if their instruments were broken. There's a trick in geology called a magnetic anomaly. It's kind of like a fingerprint. Every rock type has a signature, and once you understand the signature, once you learn how to read it, you can read the history. You can see what happened, you can see where the rock came from, how old it is, and what it's been through. Here's how it works. When molten rock cools down, when it transitions from liquid to solid, the magnetic minerals inside it freeze in place. They lock onto the direction of Earth's magnetic field at that exact moment of cooling. It's like a photograph taken in the middle of cooling, a snapshot, a record. But here's the thing nobody expects. Earth's magnetic field isn't stable. It's not fixed. It flips. North becomes south, south becomes north. Not on any predictable schedule, not regularly. Just randomly every few 100,000 years, the whole thing reverses itself. Scientists don't fully understand why. It just happens. When that flip happens, rocks that form after the flip have the opposite magnetic direction. So you get stripes, layers of normal, then reversed, then normal again, like a barcode written in stone. Different rocks form in different magnetic states, so each rock formation has its own pattern, its own signature. This is how we proved continental drift. This is how we proved plate tectonics wasn't just a theory. The magnetic stripes were the smoking gun, clean, perfect, impossible to fake. The scientific community saw those stripes and realized the textbooks needed to be rewritten. Now look at the rocks beneath the Arctic. The ones flagged by the gravity data as old, dense and wrong. When you measure their magnetic signature, the stripes don't look right. They're distorted, fragmented, reversed in ways that normal seafloor spreading can't produce. They don't have the clean pattern of young ocean floor spreading symmetrically from a mid-ocean ridge. They have the messy pattern of something old, something that's been through multiple cycles of heating, cooling, and deformation. Something that's been broken and stressed and pushed around by tectonic forces over hundreds of millions of years. Think of it like a scar. The rock has basically written its entire autobiography in magnetic form. Ancient rocks have complex magnetic signatures because they've survived so much. They've been heated and cooled and buried deep and brought back to the surface. They've experienced earthquakes, mountain building, rifting, and collision. Each event leaves a mark. Each event adds to the complexity. And the autobiography reads, continental, old continental crust, the kind that takes hundreds of millions of years to form and thousands of millennia to deform. Geologists have a name for this region, the High Arctic Large Igneous Province. For years, people thought it was just a volcanic area. Interesting, but not special. Just some flood basalts and submarine plateaus, lava flows from the mantle, underground volcanoes, cool geology. But nothing revolutionary. But what if it was more than that? What if it wasn't a volcanic province at all? Up until this point, scientists were still trying to explain the Arctic using normal geology. What came next made that increasingly difficult. What if it were the ghost of a drowned continent? What if the volcanic activity was just the death rattle, the final throes of something breaking apart? Here's the thing nobody paid attention to for decades. The Arctic ocean floor isn't flat. You'd think it would be. An ocean floor should be this smooth, featureless basin, boring, uniform, predictable, but it's not. It has mountains. Underwater mountain ranges that rise thousands of meters from the bottom. Underwater valleys, underwater plateaus. A landscape as complex as anything you'd find on land, just hidden beneath the ice and dark water where nobody could see it. There are these major ridges. The Lomonosov Ridge is the most famous, nearly 1,800 kilometers long, running from the continental shelf of Siberia all the way to Greenland like a spine cutting the Arctic in half. A mountain range in the middle of an ocean. You could hike along it for weeks and see nothing but ridge and valley. Except you can't because it's underwater beneath hundreds of meters of ice. Then there's the Alpha Mendeleev system running parallel on the other side, another major underwater mountain chain, two massive underwater mountain ranges with a basin between them, the Makarov Basin, a valley in the middle of an ocean. For decades, geologists had an explanation for the Lomonosov Ridge, a clear explanation, the kind that gets into textbooks. It was a piece of continental crust. It broke off from Eurasia around 56 million years ago during the Eocene, which was a warmer period in Earth's history. It drifted north, got stranded in the Arctic. Makes sense tectonically, makes sense geologically, explains everything, except when you measure how thick the crust is under the Lomonosov Ridge, when you actually measure the crustal thickness, it's way too thick for that story. Way too thick for something that supposedly drifted away 56 million years ago. Continental fragments that drift away thin out. The crust gets stretched like taffy being pulled from both ends. It should be paper thin by now, instead it's thick, dense, heavy. Same problem with the Alpha Mendeleev ridges on the other side of the basin. Too much crust. Wrong kind of crust. The density signatures were all wrong for the ocean floor. The magnetic patterns don't match what you'd expect from seafloor spreading. And in between them, in the Makarov Basin, the magnetic patterns weren't clean like normal seafloor spreading. They were broken, fragmented, twisted, like the crust had fractured and subsided, like it had come apart and never quite settled right. Like something broke down there and tried to heal, but never quite managed it. Two major ridges, both too thick, both are carrying the wrong signature, both are pointing at the same answer, both are telling the same story. Something big had come apart down there. Something had sunk slowly over geological time. Something enormous had died in pieces. When you take all of it together, all the gravity maps and all the magnetic data and all the crustal thickness measurements and all the seismic tomography images, when you feed it all into tectonic reconstruction models, something starts to emerge. It's not clean. Geology never is. Real reconstructions always look like a puzzle. Someone assembled with missing pieces, ragged edges, damaged corners. Parts of it were basically erased by volcanic activity. So recent and so violent that it barely resembles what it was originally. Messy, incomplete, imperfect. But it's coherent, it has internal logic, it makes sense as a whole, it tells a story, one narrative. What it shows is a continental platform, real continental scale. Not a small fragment, not a micro-continent you could barely see on a map. Something that actually stood above water once. Something with geography, with landscape variation. Imagine standing there 150 million years ago, rivers flowing, mountains in the distance. A landscape that looked permanent, a landscape that would eventually disappear beneath an ocean, with mountains and valleys and plains, with the kind of structure you'd expect if life actually walked on it, if rivers flowed across it, if the weather moved over it, connected to Greenland at different times, connected to Ellesmere Island, connected to Siberia, part of a larger Arctic ecosystem. All of these landmasses were once connected, one continuous platform, and then it didn't just vanish, it broke apart, over millions of years, in pieces, slowly. The Atlantic Ocean started opening up 180 million years ago. This is the big story. Pangaea was pulling itself apart. That supercontinent that had all the landmass clustered together was fracturing. That stress radiated outward like a crack in a piece of glass that doesn't stop where it started but keeps traveling along the weakest seams. The stress reached the Arctic platform. Rifts developed, fractures appeared, volcanic activity intensified. The crust didn't snap cleanly as you might expect. It was torn, slowly, over millions of years, pulled apart from below by mantle convection, fractured from the margins inward by tectonic stress. The thermal support underneath was withdrawn piece by piece. The platform lost its buoyancy. It started to sink, and it sank. What's left now when you strip away the ocean and the sediment and the ice are the bones, the skeleton, the remains, the Lomonosov Ridge on one side, the Alpha Mendeleev system on the other hand. Fragments of ancient, thick, dense crust are scattered across the seafloor like pieces of something that was once whole and is now barely recognizable as ever having been a single thing, like the broken pieces of a statue, like the shattered remains of something that mattered once. And the gravitational signature of all of it combined, the signal that satellites are reading with enough precision to map in detail, is the signature of a continental graveyard. A place where something enormous died slowly and left its skeleton behind in the dark. A place where an ancient world came to an end. I want to be careful here. This isn't fringe stuff. This isn't pseudoscience. This isn't people finding lost civilizations under ice shelves or making wild claims without evidence. This is mainstream geology, getting revised at the textbook level. The evidence has been building for years in peer-reviewed literature, accumulating quietly, getting stronger. The new satellite data just made it impossible to ignore anymore. Tectonic models are being rewritten, not at the edges of the discipline, not in fringe papers nobody reads, at the core, at the fundamental level, at the level of how the maps get drawn, what gets written in the textbooks, and what gets taught in classrooms. This is foundational stuff changing. But why does that matter? Why should you care? Because the Arctic isn't static. It's not a frozen, unchanging record sitting still while we slowly figure it out from a safe distance. It's changing. Right now, faster than anyone predicted. The climate is warming, the ice is retreating, everything is in flux. The ice that sealed this world away for tens of millions of years is retreating. Every year, the pack ice gets thinner, the open water season gets longer, the seafloor becomes slightly more accessible, slightly more visible, slightly more reachable. Researchers who used to wait years for a single survey window can now plan multiple expeditions in the same summer. The Arctic is opening up, the archive is unlocking. Every season of open water is another page turned in an archive that's been locked shut longer than the human species has existed, locked shut for 56 million years. Every research vessel that goes north reads another line in a record that nobody's ever been able to read before. Every sonar reading, every sample collected, every measurement taken. The magnetic data is getting better. The sonar maps are getting clearer. The gravimetric imaging is getting more detailed. The picture is coming into focus. In the episodes ahead, we're going to explore what those pages actually say. We're going to read the story written in the geology of the Arctic. A story about a continent that was there and then wasn't. A story about how this planet reshapes itself over timescales that make human history look like a blink. A blink of an eye, a moment. We're going to see what the satellites are seeing. We're going to understand what the rocks are telling us. We're going to piece together a narrative that's been hidden for tens of millions of years, just waiting for the right tools to finally read it. Now, in this video, I've been telling you about something almost nobody talks about. A world that sank, a continent that broke apart and fell into the deep. Evidence that's been hidden in gravity readings and magnetic signatures for millions of years, waiting for us to develop the tools to read it. Waiting for the right moment when technology, access, and scientific understanding all converged at the same time. And that's just the beginning of what's down there. Because the Arctic wasn't always the edge of the world. It wasn't always the frozen frontier, the place where maps ended, the place where the world stopped. It was once very near the center of it, the center.